Thank you very much, Kati. Thank you very much to the organizers also for the invitation to speak in this conference. So I'm very honored to speak in this wonderful place to this distinguished audience. Sorry. Right, so when first Lotzi wrote to me about this conference and about the possibility of speaking here, he suggested that I speak about sparse regularity. But in view of the very recent developments that Jacob spoke about and other developments in sparse regularity for random graphs, so I switched topics. So this is some kind of a backup talk. So if I had spoken about that, I would have been in a situation of presenting some open problems that had been solved in the previous talk. So that wouldn't have been very good. But anyway, so I'll talk about limits of permutation sequences. Computer permitting. Okay. Oh. Oh, sorry, this is more serious.
It's not even a Windows machine. That's Jennifer.
Oh.
Try rebooting.
Ah. Oh, very good.
Probably push, there is a dim button on the pointer or something.
Okay. Oh, that was exciting. Right. So this is joint work with Carlos Gustavo Moreira from Rio de Janeiro, Carlos Hoppen, Porto Alegre. Porto Alegre is somewhere really in the south, close to the Uruguay in Brazil. Let me skip the Hungarian for a little bit. And then Houdini Menezes Sampaio, who is now in Fortaleza, which is really up north next to the Caribbean in Brazil. Actually, so the four of us approached this through, we're kind of combinatorialists. So we approached this problem, this area, through regularity. And then we had two papers on this. And one of the referees of one of the papers kind of wrote a very nice report for us. And he's some very young and energetic. He also said, well, you know, you quote this other paper of yours, and I read that one also, and I wrote a report for you for that one. And this turned out to be Bola Ashrat, who actually showed us a different way, a more probabilistic way of approaching this. You won't see so much of the approach itself, because I won't so much talk about the proofs, but maybe this will explain a little bit why we do certain things in certain ways. Anyway, so yeah, there's nothing too exciting about the outline of the talk, but so the main thing will be that I will talk about these limit permutations, and I'll talk a little bit about property testing. I think, so most of the things that have been done for dense graphs can be done for permutations, but there is still some annoying problem in property testing. So maybe if some of you gets interested in this, I would be very happy. Okay, so as I said before, we have one kind of regularity approach, and this was based on a regularity lemma for permutations, which was developed by Joshua Cooper in 2006. So Joshua was a student of Ron Graham and Fan Chung. And then, so this probabilistic approach here is just to say that you can do this more in the kind of analytical world. Right, so let's start with setting up some notation. So when I say a permutation, well, a permutation is just, permutation on brackets n is just a bijection from brackets n to brackets n. And if I talk about this permutation, I mean this function here. So which takes 1 to 4, 2 to 5, and so on. So this will be my notation, right? Okay. Now I should say what I mean by a subpermutation of a permutation. And I think it's best if you just look at this example. So I claim that this, in my definition, this permutation tau is a subpermutation of sigma. So tau is contained in sigma. Because, for instance, you could look at these red elements in sigma. And if you look at the shape that they form, that's the shape of 3, 1, 4, 2 in the following sense. You have the second largest first, and then smallest, very largest, and second in this permutation tau. And that's what you see here, 5, and then you drop down to 2, 7, which is the biggest, corresponds to 4, and 3, which is the second smallest, right? So 2, 3, that's 1, 4. So that's what I mean by permutation containment. And you see that tau occurs in this other place also. You could pick indices 1, 2, 4, 6, right? You get the number 6, 2, 7, 3, and they describe the same shape, the shape 3, 1, 4, 2. So tau occurs at least twice in this permutation sigma. Okay, now this slide is here just to try and make the point that this notion of permutation containment is kind of leads to interesting things. They don't so much have to do with what I'm talking about. So let me, well, maybe the first two things I do want to stress. So I will say that a class of permutation, a collection of permutations, is hereditary if it's closed under taking these subpermutations, right? So if I define my hereditary class that way, then it's clear that you can also characterize by the minimal elements which are not in the class, namely any hereditary class is of this form here. So you specify some set of forbidden objects, F, and then you say, well, I only take permutations sigma which do not contain any member of this forbidden class, right? Okay, so this is the class of, so these are the hereditary classes of permutations. Now, so here are some kind of random remarks just to try to say that this notion of subpermutation is interesting. So there is an infinite anti-chain under this containment. It follows, for instance, now that if you take this anti-chain and take any subset and form this 4F, you get a different hereditary class. So there are lots of hereditary classes of permutations. You can also, people have studied what is sometimes called the speed of a class. So you can think of this family, you can fix this P, a class of permutations, and then you can count how many permutations you have at each level. So how many length k permutations you have in P, and you can consider this function. This so tells you how much this class grows, right? So this is the speed of growth of this class. And a very famous conjecture, Stanley-Wolf conjecture, and now theorem of Klazar, Marcus, and Tardush, says that this speed is there are very strong constraints on the speed. Namely, so for instance, if you have a class which is not the whole class of permutations, so if it's not n factorial, if you forbid at least one permutation, you already drop down to exponential speed. So this is, as I said, this is just to, maybe it's unnecessary for this audience, but it's just to try and say that this notion of permutation containment is of interest and kind of reveals interesting structure in theorems. Okay, so now we know what we mean by a permutation being contained in another. Let me do now a frequency count. So given permutations tau and sigma, we write lambda of tau comma sigma for the number of times tau occurs in sigma. So this number could be between 0 and n choose k, maybe every, maybe I didn't say, so tau has k, is a length k permutation, and sigma is a length n permutation. right? So maybe every choice of indices gives you a copy of tau, or maybe none. So this number, lambda of tau sigma, is between 0 and n choose k. So we normalize so that you get a number between 0 and 1. Okay, so this is the frequency of tau in sigma. And we just copy the definition of convergence of dense graphs. And we say that a sequence of permutations sigma n converges if all of these frequencies converge. So you test every fixed permutation tau, you get a sequence of numbers, and you want that sequence to converge. Okay, so this is just the exact copy of the notion of graph convergence, dense graph convergence. It will be convenient for me to say, to define, it's a simple notion, what I mean by a random subpermutation of a permutation. So we fix, actually maybe again an example is much easier. So suppose you have this permutation sigma of length 10, and so n is 10. And then you want to generate a permutation of length 3, so k equals 3 in this case. You want to generate a permutation of length 3. Well, there's an obvious way of doing it. You just sample 3 indices, 3 distinct indices, in this case 2, 5, 9. So you look at the positions 2, 5, 9 in the permutation, in the big permutation sigma, and you look at the shape. And the shape is biggest, smallest, second, middle, right? So you get the permutation 3, 1, 2. So this is just what I mean by sampling a permutation of length k from a big permutation sigma. And it's clear, or it should be clear if the definitions are clear, that this frequency is just the probability that this random permutation, k permutation, is equal to tau. The frequency of tau in sigma is this probability. So looking at this in this way, the convergence of sigma, of the sequence sigma n, can be thought of in the following way. So you fix the length of subpermutation, you fix k. Then every sigma n gives you a distribution on length k permutations. This is the distribution, right? And you want for every fixed k, you want this sequence of distributions to converge. That's so this is nothing new. Lotzi mentioned this in his lecture. Well, it's right. Okay, so this is the notion of convergence of permutations. And the whole, of course, we could just do some abstract nonsense and create some limit, but we want to do it in some more natural way. So we want to put all these limit distributions dk. So dk is the limit of this sequence of distributions. We want to put all these dk's in one object in some way that hopefully one can use for other things. And so we are trying to find this object. Okay. And to do that, we go to functions. And one way of representing functions that will be convenient for us is the following. So this is very natural. So let's see. So here's an example. So you have this permutation 2, 4, 5, 3, 1. This is actually the graph, right? So 2, 4, 5, 3, 1, right? And you do this in the unit square. And so this is a step function, 0 on the white, and blue is 5. You just make it that way. That's the normalization that we want. Okay. Once you have this, so this function clearly represents this permutation sigma. Now we do the following. We integrate, so on every fixed x, we integrate from bottom to top, and we get this function. So as you go down, you go up here on some vertical line, you are 0, and then you meet one point of this step, yeah? So you linearly grow up to 1, and then you remain constant at 1. So you get this object when you integrate this way. So this is the function z sigma, which we will use to represent the permutation sigma. Now let's look at some simple properties of this function. So this function starts at 0 here, and then grows to 1 as you move up. So this is written here. well, on each, for every fixed x, this is non-decreasing. And also, you have this kind of mass condition. If you fix, so this integral is in the other way. So if you fix some y, so this height, and then you integrate vertically, you get y. This is just because you started with a permutation. I hope it's clear. So at the beginning here, you get 0, and then as you grow, you get, you grow linearly, and then linearly again, and so on. Okay, so this is what you get with this construction. And in fact, we define the limit permutations this way. So we say that, so for us, a limit permutation is a measurable function on the unit square, taking 0 and values in 0, 1. And we want that for every x, so if you look at vertical line, you get a cumulative distribution function. That is what these things are, right? So these two properties. And also, for every y, we have this mass condition, which was the third condition in this construction here. Right, so this is our definition of this limit object for permutations. And, right, so before, yes, so, okay, so that's the definition. Now, let me also define, yes, I have to do this now. So I have to define random subpermutations of Z. So given some limit permutation Z satisfying those conditions before, the two properties before, I would like to define how to generate length k permutation from it. So I want to define sigma of kz, this random length k permutation. And the process is the following. So you first randomly generate k points here, and you label them in increasing order, x1, x2, x3, and so on. Next, we recall that zxi, this function z, has the property that if you fix x on this line, you have a cumulative distribution function. In other words, for every xi, x3 here, you have a distribution on the unit interval. And then we generate a random point here in each of these vertical lines according to those distributions independently. So these are the points that we got. So for instance, x1 is here, and so on. And doing it this way, you see a shape, right? And this is the permutation that we randomly generated. So the shape here is 3, 2, biggest 4, and smallest 1, right? So this is the definition of this random permutation sigma k z given z. Okay.
Can you have ties?
No, no, you cannot. Yeah, so you have to show that on you have no 2 points on the same height. So you have to show this from the conditions of the limit. Okay. Yeah, so, right, so we define this random subpermutation. Yeah, so there's an extra bracket here, sorry. So we defined a length k subpermutation of z. The probability that this is some fixed permutation tau, we define to be the frequency of tau in z. So we have a distribution on length k permutations for any k given z, right? Right, so this is our definition of subpermutation density in this continuous object. And the theorem that you would expect is the following. So given a permutation convergent permutation sequence, we don't embed this in the definition, so we say that the lengths go to infinity. If they don't, then actually it follows that the sequence is constant, so maybe they should be embedded in the definition. Anyway, so I have a sequence of permutation sigma that grow to infinity, so they become bigger and bigger, and it's convergent. Then there is an object z, as we defined, such that all the frequencies, all these limits, which we know exist by definition, are captured by this object Z. So another way of saying this, perhaps a more compact way of saying this, is the following. So Z is that object that encodes all the limit distributions dk that we had before. Right, so if you remember, I said that we can use each of the elements of the sequence sigma n to define the distribution on length k permutations. They all converge, and they all now are captured here in this. Okay, so this is the first theorem that you would like to prove in this context, and one is able to do that. Now, there are kind of natural things to do next, just following the dense graph case. Let me talk about this thing first. So this class of objects, actually, they're all necessary in the sense that for any limit permutation Z, there is a sequence of permutations converging to Z. And as in the graph case, the way that you define random subobjects of Z suffices. So if you remember, the sigma nz is the random permutation of length n that we can generate from Z through that process of generating the x's and then the y's. That is so if you consider this sequence, you get a sequence which converge to Z in probability with probability 1. Okay, so all the Z's are necessary. And also, it's harder in the graph case, it's simpler in the permutation case. Since you cannot permute things freely, the uniqueness kind of follows more easily. So the object is kind of more constrained. So it's easier to prove uniqueness, and one is able to prove that. Yes, okay, so in a way this kind of copies the graph case to permutations in the expected way. Let me say something. So this object Z and so on was the natural thing to arrive at if you think about regularity of permutations, about which I'm not really talking, but you kind of get pushed into this direction. Z becomes a natural thing to have. But maybe a better way, a cleaner way of looking at it is the following. So if you remember how we generated random permutations given Z was the following, right? So you chose in the x-axis, you chose uniformly at random k points, and then you looked at those k distributions and generated the y's, right? And then you look at the shape. Actually, what you're doing there is just the following. You're just generating lots of points from this unit square, and you're looking at the shape that this describes. Right, so we have done this. So we described how to generate a point from the unit square given Z. And the thing that to notice is that, well, X is certainly uniform. That's how we did it. But because of that mass condition that we imposed on our limit permutations, namely that when you integrate this way, you get the height y, it follows that y is also uniform on the unit interval. So you have a distribution on the unit square which has uniform marginals. So maybe that's a better object. But actually, they are kind of the same. So we described how to get xy from Z, but you can also construct Z given xy. So this is the regular conditional distribution of y given x. Right, so this is another way of looking at it. Maybe this is a cleaner way. But anyway, so they're equivalent. Now, next. So far, I have said something about the convergence, but I haven't said anything about distance. So let's look at that side of the theory. And now, again, as I said, based on the regularity notion of Cooper, it's natural to define the following distance, which we call the rectangular distance between permutations, sigma and pi. So let me try to explain this definition. So we have sigma and pi permutations on brackets n. So we do the following. We consider intervals S and T. So S and T are intervals in brackets n. And we are interested in where sigma sends S and where pi sends S. And we intersect it with T, right? And we kind of check the difference. This is a kind of linear quantity we normalize by n. So for instance, if pi is the uniform distribution, pi is the random permutation, so pi s intersection t would be of size of s times size of t divided by n, right? So you would be measuring how much sigma deviates from this if you measure distance to a random permutation. In fact, if you replace pi, or if you replace this quantity by the expected value of this when pi is random, you get the notion of discrepancy defined by Cooper. Right, so this is the proposed notion of distance between permutations, which mimics the cut norm in the case of graphs, the cut distance. Okay, let me talk about another distance, this is the overlay distance, which maybe combinatorially is more interesting, and it would be nice to, yeah. So this is another notion of distance, and maybe this is the more interesting notion of distance. And this is the overlay distance. So here's the definition. We have two permutations, sigma and pi on brackets n again. And we are interested in this set of relative inversions. That only means the following. So for every pair of indices I and j of brackets n, you check what sigma does to the pair and what pi does to the pair. Maybe sigma swaps and maybe pi also swaps. In that case, they agree on this pair. But it could be that one swaps I and j and the other one doesn't. In that case, you count one. You say that that's a relative inversion. So we normalize this relative inversion by n choose 2, which is the maximum it could be. So you get this distance sigma tau, which is Kendall's tau distance, maybe without the normalization. But anyway, so this I think would be, so this is an interesting distance to work with. And I think this would correspond to the added distance for the graph case. Now, the notion of limits for permutations that we described actually matches, sorry, before I say that, so apparently I have to say how these two distances relate. So let's see. So this is the overlay distance. So this counts the relative inversions. And this other guy here, the rectangular distance between permutations, check, well, some more complicated thing. So you look at big intervals and you compare how sigma and tau map them, right? Now, so one remark is that if this distance is small, dk is small, the overlay distance is small, then this rectangular distance is small. So let's quickly kind of try to see this, at least have some idea. So this notion of distance asks us to compute this. So if you say that this number is big, that means that there are two intervals s and t on which sigma and pi disagree a lot, right? Maybe it's even easier to kind of think, yeah, okay, so they disagree a lot. Now, right, so, and you are trying to know whether this implies that there is a lot of inversions, relative inversions between sigma and pi. And the answer is yes, there are lots of relative inversions because actually maybe it's easier if we just think, let's compare the distance between sigma and the identity. So this would be S intersection T. So it should be in one way, but then you deviate. So that means that you kind of have to flip lots of images of sigma to match the expected quantity here. Yeah, maybe this was worse than, maybe it was not a good idea to try. But anyway, right, so it is a fact that if you have small inversion distance, then you have small rectangular distance. But as in the graph case, the other relation doesn't hold. So this is what I say here. So if it could be that this number is small, but this overlay distance is big, and the example is the same as in the graph case. So if you take two random permutations, sigma n and pi n, the rectangular distance will not see the difference between them, as in the graph case. But the relative inversions will be very big, right? So for every pair, you expect them to disagree with the probability 1/2. So one distance dominates the other, but not the other way around. And as I started saying, but now I should say again from the beginning, the notion of distance that matches correctly the definitions of convergence and limits that we had is the rectangular distance. So a permutation sequence, sigma n, is convergent if and only if it's Cauchy with d square. Of course, I skipped the definition of this distance d squared for permutation of different lengths, but one does the same thing that one does with graphs, right? So you first look at the permutations, represent them as functions, and then in the functions you can write the rectangular distance. Okay, an expression that works for any two functions. Right. So this is again one theorem that you would expect, and you would it would be your duty to prove given the graph theory for permutations, and one is able to do it. Now let me change a little bit and move to property testing. So in this area, the idea is the following. So you have some property P, and you would like to distinguish between two extreme cases, namely the case that sigma is actually sigma satisfies P, or sigma is far away from satisfying P. So there's this notion of far here, which we have to explain, but you want to distinguish between those two cases. Sigma satisfies P, or close to satisfying P, but let's say sigma satisfies P, and the other case, namely sigma is very far from satisfying P. And the question is, in property testing, is whether you can check this in some very efficient way. So for instance, in a way that would not depend on the size of the object you're examining. So you have sigma. So in the case of permutations, you could have the following definition. Take sigma, and suppose the only thing you're allowed to do is to take a random subpermutation of length k. So you're allowed to generate this sub k sigma, and k is of constant size. And suppose, this is what you're allowed to do. Can you distinguish between being in P and being far away from P for interesting properties P? So that's the question. Okay. So this is, now this slide contains, yes. Yes.
There are two ways to interpret what you just said.
Okay.
You mean that I sample the permutation at a fixed number of points, or I given the statistics of so let's say k is 10, I've given the precise
no, I don't.
distribution on S10 that you get from the...
No, I just sampled sub 10 sigma. And from this, I would like to know. Or if you like, I have an algorithm that has a behavior given a distribution on S10, and I want to decide yes or no. and I sample and I want to decide. So I don't see all, yeah. So I just sample one and I want to say yes or no. Okay. Now in this slide I have two definitions. They have to do with this W and S and W and S. And this has to do with the fact that in my previous definition I wasn't explicit about what I mean by far, so namely this. So we are trying to distinguish between these two cases, being in P and being far away from P. I could measure this distance according to any distance. And so there are two possibilities. So I measure with respect to the rectangular distance, and I measure with respect to the overlay distance. So this definition here, if you read this line, is the definition of weakly testable, and if you read this line, is strongly testable. And if it's correct that, yeah, that's probably correct, that the distance that is more interesting is this case, this strong testability. Yeah, right. So there are two notions, and maybe the more interesting is the strong testability. So let me say the definition. Let's go over the definition. So we say that it's weakly or strongly testable through subpermutations. A property P is weakly or strongly testable if the following holds. So we are given some parameter epsilon at the beginning, and then we have to give some number k, which depends only on epsilon. And then in this game, we are only allowed to look at subpermutation of length k, right? And what you're allowed to do is to sample a length k subpermutation of the input sigma. And this algorithm should be able to say, looking at this, should have the following behavior. If sigma satisfies P, then with high probability, this should satisfy P also. So when you take a random subpermutation, you should, which satisfies P, then you should say, yes, sigma satisfies P. And also, in the other extreme, namely, if you have as input sigma, some permutation which is far away from P, and far away we mean one of these two, then with high probability again, namely with probability 1 minus epsilon, we should see a subpermutation that does not satisfy P. Actually, it would be just a slight generalization. Maybe you would like to change what you want to check about the random subpermutation. So maybe here would be some P prime closely related to P. That would be allowed also. But I wrote it this way just to simplify. Okay. So, we say that the property is testable in the weak sense or strong sense if there is an algorithm. Yeah, maybe I oversimplified it. So if there is an algorithm, so if there is some P that you can put here, if you sampling this sub K sigma, you can see whether or not sigma satisfies P or is phi. Okay. Now, it is standard now from looking at the graph case how to prove that every hereditary property is weakly testable. Namely, if you measure distance according to the rectangular distance, then it's clear, then one can prove this. But unfortunately, something which is great in the graph case is that just pushing it a little bit more, you can also prove strong testability, namely testability with respect to the edit distance. And unfortunately here this is some embarrassing problem, so it's still a problem, so we don't exactly know. And this would be some nice thing to do here. Right. Now, next, let me say something about removal, and then I will go back to testing, because these are very tightly related. So now I have to say what it means to remove permutation, subpermutation, some given permutation tau from some big permutation sigma. And the definition is a little bit maybe weird, but it's like this. So we have some tau and some sigma. Tau is small and sigma is big. And you would like to destroy all copies of tau in sigma. You'd like to remove all copies of tau in sigma. So what you are allowed to do is to specify a set of pairs of indices. So it's like specifying a graph on the index set. And what this graph should do is the following. Every copy of tau has to contain an edge of this graph, right? This is what we mean by removing. So again, a set S removes all copies of tau in sigma if every copy of tau in sigma uses both elements of some member of S. Right, so this means that you could, so S could be spanning, could be a spanning graph, contains all points. But it destroys only the permutations, tau copies of tau, that contains edges of this graph. And so Cooper himself had already this theorem for the case of removing just, in the case in which this F is just a single permutation. You have to do some extra tricks if you want to consider infinite families. So if you want to consider, hereditary property, general hereditary properties, so things of type fob F for arbitrary F for F infinite, then you need some extra tricks. And but one can do that. So Matthias Schacht observed that one can do that using the methods of Cooper plus some extra tricks. And the removal lemma goes as follows. So F is some collection of permutations that I want to. Those are the forbidden guys, maybe. Then, there are several constants here. So there's for any eta, there is some n0, and maybe this m is more important. And this C0 shows up here in the conclusion of the count. And the removal is like as follows. So if you have a large permutation, and if this large permutation has the property that to remove every member of F, you have to pay a lot. Namely, you have to remove this many pairs. So this guy has to be as big as this. So you have to remove a dense graph to remove all copies of every member of F. Then actually there is one single member of one forbidden guy, right? The ones that you fixed, that occurs many times. So that occurs n to the m times. And m is the length of this permutation. Okay, so one is able to prove this removal lemma, which is great, which is general. It's for arbitrary hereditary properties, if you like. But in a way, what is a little bit disturbing or something that one would like to do is the following, right? So here, the process of removing a graph or removing copies by specifying a graph that you kind of delete looks artificial maybe, and maybe kind of it's something different, right? So you'd like to remain in the class of permutations, and you'd like to work with them and not with permutations with some forbidden pairs. And so here is a property which would nicely solve this. So I state it as a problem. And this is very similar to what one proves in the graph case to prove what I called strong testing. So let's see. So we have here a hereditary permutation property, or if you like, you have some family F, possibly infinite, of forbidden permutations, and you're considering all permutations that do not contain any of them. So that's P. And I would like it to be, I would very much like the following to be true. So for every, I'm interested in this distance. So we have P, and now I would like to measure distance of permutations to this property. So I'd like to measure distance from sigma to P, distance from sigma to P, and I would like the following to be true. I would like it to be true that to guarantee small overlay distance to the property, it's enough to have small rectangular distance to the property. I would like this to be true. This you can kind of think about. Right, okay, so this
It's the how many edges you have, how many.
right, how many pairs you have to invert to
get
yes,
something.
right, that's exactly right. But since, yeah, but somehow they are different objects, you cannot just freely swap, yeah, anyway, so. And then if one could prove this, then this strong testability would follow. And also it would give some different proof of the removal lemma. So for instance, this is quite, I find it interesting, even if you have some property P which is very simple, so you forbid some pattern. And on the one hand, actually, yeah, so let me say something which is not on the slides. So the removal lemma will tell you that with this business of forbidding a graph, so this S is the edge set of a graph, right? By forbidding some, if it's true that you have to forbid a thick graph, then you have many copies of this fixed permutation tau that you're looking at, right? This is what this theorem says. But now, as I said, I kind of don't like so much this idea of forbidding pairs, forbidding a graph. I would like to invert and destroy copies of tau. And the question is, so can one prove, is it true that if you have to, so which way around? So is it true that, which way around? So is it true that if you have to, yes, if you have to invert a lot to destroy copies of tau, is it true that this graph has to be thick? If this were true, then you would have it. Anyway, so I think the message here is that there is a nice removal lemma, but the game that you play in this removal lemma is not quite maybe the game that you would like to play with permutations. Namely, you would like to invert to destroy, or yeah, to destroy copies of a permutation. And the question is, how efficiently can you do that? If you know that the number of copies of this given permutation, forbidden permutation, the guy that you want to destroy, is actually small. Right. That's a nice, purely combinatorial problem. Okay. Now, I will... so this is what I had to say. And as I said at the beginning, so very interesting, very exciting things kind of happened in the area of regularity, of sparse regularity. And now, so I switched to this talk. And then I heard that, so some very nice, it's a problem that I think many people liked a lot. So it's a problem by Ron Graham. And so this was solved, and it's related to this. So Dan Crowell and Oleg Pikurko solved this problem of Graham, which I would like to describe now. So if you remember, given sigma, we can induce a distribution on length k permutations. It's just you just sample k indices and you look at the shape. That gives a distribution on length k permutations. That's I denote it this way. And Graham's question was the following. So is it true for some k that if this is approximately uniform, is it true that for k plus 1 it must also be uniform? This on its own kind of sounds crazy, but in the case of graphs, this is true. So for graphs, if you know frequency counts of graphs on 4 points, you kind of know for 5, right? Which is really very interesting. And the question is whether permutations would behave the same way. So it was known, it's easy to see that 2 is not enough, 3 is not enough. Well, it's easy to see that 2 is not enough. For 3, you have to work. And this was known early. even at the time of the conjecture, and the conjecture was launched or question was launched. But now, Dan Kral and Olga Pikurko were able to prove that K equals 4 is sufficient. And the proof the final version of the proof is a very elegant and short proof using limits, using the language of limits. They, as far as I understood, they had indications from other methods, more complicated, but they now have a very nice proof, which was put on the archive a few days ago, maybe, or a week ago. So, anyways, and this is, I think, a great result. And it's nice that this language of limits is kind of useful for this. And I will stop here. Thank you.